Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Dynamics. And in today's topic, we will see the numerical problem on one-way diffusion equation. So basically, we had seen about one-way diffusion equation. How do we formulate using finite volume method, and we had also seen for 2D, 3D also. But for simplicity point of view, or let's say basic point of view, we are solving for 1D problem. So in the next sessions, we will see for 2D problem actually. Fine. So for having a quick recap, so we have seen the finite volume formulation for a 1D element where P is a point of interest P, and west node, west node, east node, and the distances. So if we take for 1D steady compressible continuity equation, so this is what we have, incompressible. So if you take incompressible, the density will come out. So when you integrate the surfaces in between W and E, so what do we have? The integral form of equation is like, so whatever the rate of change of flow inside the control volume rho dV will be equal to, so the surface integral rho d ds. So this is the basic continuity equation. Fine. So this basic continuity equation. So for in the LHS term, what do we have? We have minus. Minus is nothing but it's a decrement. The rate of decrement of the flow inside the control volume. So here rate is nothing but dou by dt. So minus symbol indicates the decrement. So rho dV is nothing but mass, and here we have the volume integral, which is inside the volume which you see. So the conservation of mass or the continuity deals with whatever the rate of change of mass inside the control volume is there will be equal to the flux or the flow which is crossing through the control surface. So here we are seeing in terms of integral form. Okay, it's not differential form. So as I told you, so finite volume methodology, they will follow the integral form of equations. Okay, finite difference method, so they follow the differential form of equations. Fine. Now, so when I say steady, what do you mean by steady? So this term is zero. The time derivative term is not present, which is taken as zero. So the time derivative term is zero, and the what we have only the flux term. So flux term is nothing but rho v dot ds. Fine. So here when we do the surface integral of rho v dot ds, so ds is nothing but the area. So this term, when we are doing the surface integral between two surfaces, the west and east. Okay. So when we do the integration between the west and east faces, so what do we have? So rho u a into e, rho into u into a, which is nothing but density, velocity along x direction, so area at east face, minus, so rho u a w. So rho is nothing but density, u is velocity, x velocity, aw is nothing but, so the area along west face. Fine. So their difference, so we have this. Fine. So this is the basic finite volume formulation for what we have only 1D. So basically this is 1D unsteady equation. So when we see 2D continuity equation, so what do we get? So we have point of interest P, we have west node, we have east node, so we'll have north node, and we'll have south node. Fine. So we have east, west, north, south node. For 1D we have only west and east. For 2D we will have additional north and south. Fine. So here the formulation we have for 1D. So this thing for 2D, how do we do? So that will be rho u a of surface E minus rho u a of surface W plus rho and bidirectional velocity, which is v velocity a of north n minus rho v a of s is equal to 0. So these two terms are contributing for 1D. So this whole term is contributing for 2D. Right? So this is the difference which we have. So if we take 1D, so only we have rho u a e and rho u a w. Fine. This is for 1D. So for 2D, additionally we have north and for 3D, what do we have? So we have additionally, it is back. Let's say this is front. Fine. So additionally we have plus rho w. So a of front minus rho w a of back. So if we add this thing also, it will be combined 3D. Fine. So we have 1D, which is rho u a e, rho u a w. 2D, which is rho v a, rho v a. So which is of north and south. So we have 3D, which is a combination rho w a, which is front minus rho w a, which is back. So when I combine all these three, so it will be 3D. Fine. So here what is happening actually, if let us see the differential or the full form of equation. So we have dou u by dou x plus dou v by dou y plus dou w by dou z, which is equal to 0. So this is the 3D equation. So when you say 1D, so the only first term will be there. When you say 2D, these two terms will come into picture. When I say 3D, whole equation will come. So here, when we see the finite volume formulation for continuity equation for 1D, so we have only this equation. For 2D additionally, we have north and south. For 3D, we have additionally front and back. Okay, so this is for continuity equation, which is 1D steady equation. Fine. Now let's see the problem. Because so we had seen for only the diffusion or finite volume formulation for only the diffusion term in momentum equation. So for sake of clarity, the continuity equation is being explained previously, so that we use that thing in our numerical problems. Right. So here, what is the problem which we are seeing? So it is a 1D element. So basically, you can see this is 1D element. So what is 1D element actually? What is 2D element? What is 3D element? So when I say 1D, so cross section area. So this area, this area, this area, we assume it is constant. So where the length is greater than height, or you can say diameter. Fine. So that element will correspond to 1D. So 2D is of length and diameter, let's say length and height. They are of comparable thing. 3D, you will have the full-fledged, full-scale model. Fine. So this is 1D. So let's say this is your 2D. Let's say the cuboid. So we have it as 3D. So this is the difference. Fine. So now what do we have? So when we take this 1D element, for the current problem, we are estimating the heat diffusion. So what do you mean by heat diffusion actually? We have heat diffusion equation. So the temperature is actually varying with respect to x direction. So when we draw the coordinate axis, so we have this is x axis, this is y axis. So along the x axis, so the temperature varies with respect to space. Fine. So K is nothing but the thermal conductivity. So A is nothing but the area, cross-sectional area. So we don't have any source term. So source term in the sense the heat emitting heat emitting or the flow emitting entity. So when you have some temperature which is evolving particularly from this point, so with certain value, so we say that it is called the heat entity or the source term. Fine. So this is the terminology. Now for this problem, what we need to see? So we need to see the 1D steady state heat diffusion equation finite volume formulation. So we are formulating using finite volume formulation and solve them. So with different what do you say? Different number of subpoints that we take for along the element. So here, so you let us write down in let us draw in terms of the element quantity. So if we take this as A and this as B, this as B, so this is wall actually. Fine. So let us divide this into 5 points. So this is point 1, point 2, 3, 4, 5. So we have divided into 5 points. Let us take the spacing between these 2 points as delta x. So here it is delta x. So we have grid points 2, 3, 4. So these are called the interior grid points. So interior grid points or the internal grid points, where at 2, for the 2, what is the neighboring point? What is the west node? We have 1 as the west node and 3 as the east node. But whereas for grid point 1, so we have wall. Okay. So let us take this as our delta x by 2 spacing. And here also we have delta x by 2. So here we have only the wall. So therefore we need to apply wall boundary condition. Here for the B, the right side. So for the west node, at the left hand side you have the wall. For the right hand side you have B, which is wall. So which is acting as a boundary condition, which is stationary. Okay. So using this formulation, we need to solve the problem. So let's do it. Right. Now here, what do we have? So here we are dividing the grid into 5 elements. Okay, and let us take the delta x as 0.2. Fine. Now, so as we have seen, so let me draw it again. So we will draw in big picture. So this is the rod. Fine. This is boundary A. This is boundary B. Fine. So this is point 1, 2, 3, 4, 5. So this is the one. So between A and 1, the spacing, let us take this as delta x by 2. So here this is the spacing which I am talking. Now here in between these two, so we will take it as delta x. So between 2, 3, 4, or let's say between 1 and 2, 2 and 3, between 1 and 2, 2 and 3, 3 and 4, 4 and 5. So we have the spacing as delta x. These are delta x. And similarly at the end, here we have delta x by 2. Fine. So this is the difference. Now what we are happening actually, the equation. So this is the basic equation which we have. So Ke, this is this term we already seen. This is called A of P term, and this term which is called AW term. So this term we call it as AE term. Fine. So when you have the wall, so what we assume is that so we take the source term this as 0. Okay. So in this source term we'll take this 0 on the left boundary. So we'll see it in detail. So which is A P TP is equal to AW TW plus AE TE. So in this way we are formulating it. Fine. So in this way when we formulate it, so what do we have? So it is in the form of linear entity. Now AP TP, A is nothing but this constant. Fine. So KE delta x PE into AE plus KW delta x PW into AW. So this entity we have. Fine. So then after what do we have? We have AW. So AW is nothing but for the west node. Next we have AE, which is nothing but east node. So when we are solving any particular kind of problem in the finite volume formulation, the main important thing what we need to see is, so what are the neighboring points. So if it is at the west node, so we have a wall or the boundary. For the east node, for the point 5, so we have again boundary. So this formulation cannot be seen for the uh, points 1 and 5. Okay, so this is what we have. So yeah, as we have seen, so basically what do we have? So as I told you, AP TP, which is AE TE AW TW. Okay, so AE is nothing but what? K by delta x into A, K by delta x into A, which is nothing but AE AW. So AP is nothing but, so AW plus AE. Fine. So here the if the area at the west side is changing, so we have this. Fine. So if we want to see what happens at the west node, so let's say node 1 in the sense you have point 1. So for the point 1, so we have boundary A, and here you have 2. Okay. So how do we do the formulation? So we have K by delta x into A, which is of T1 minus K by delta x into A of TA. So in this way it will be there. Fine. So the remaining the boundary it is 0. So when we rewrite, this formulation will change in this way. So since we have what is it? This is west node, okay, and this is nothing but let's say east node. So you can take it as 2. So E, or you can keep it. Fine. So similarly, so when we when we write down and rearrange, so what is happening is, so let us write down the equation in detail. So we have, like let's say A2 TP is equal to A2 T2 is equal to A1 T1 plus A2 T3 A3 T3. So this is the equation. Fine. So this is what we have. Next we have A3 T3. So which is nothing but, so how do we have actually, so if we give in terms of index notation, so A, let's say this is I, Ti, which is equal to A of I minus 1, T of I minus 1 plus A of I plus 1. So we have A of I plus 1 into T of I plus 1. So this is the generalized equation where I value changes in between, let's say from 1, what happens, so let's say we have 5 points. I value will go from 1, 2, 3, 4, 5. Fine. So this is what we have. So let's actually write down here. So what are the equations and how do we frame the matrix? Fine. So when we take, which is A2 T2 is equal to A1 T1 plus A3 T3. Fine. So this is the equation 1. Next, when we have the point. So let us actually first write down or draw the node technology. So this is 2 and this is 1. This is 3. So basically this is the west node here. This is the east node here. This is the point of interest P. Fine. Okay. So this is what we have. Next we have A3 T3 which is equal to A2 T2 plus A4 T4. So here how the diagram will change. So here 3 is the point of interest P and 2 we have which has west node and we have 3 which has east node. Fine. So we have seen 2, 3. Now the last one is 4. Now if you see A4 T4 which is equal to A3 T3 plus A5 T5. So again if we draw the diagram, so what do we have? So here this 3 will be the west node and 4 is the point of interest P and next this 5 will be east node. Fine. So these are the discretized equation for the nodal points 2, 3, 4. Okay. So which is A2 T2 is equal to A1 T1 plus A3 T3. A3 T3 is equal to A2 T2 plus A4 T4. Next A4 T4 is equal to A3 T3 plus A5. So this whatever formulation we have written, so it is done for 1D element and using finite volume formulation. Fine. So this is what we have. Next, so when we rearrange, what happens actually we have written in form of matrix. Fine. So in form of matrix in the sense what? So when we take this, so how do we write in matrix form? So we will have 5 elements. So we will write in terms of A of T is equal to some T. Fine, we will write in this form. So what is A? A is nothing but the coefficient matrix. So coefficient matrix which is A1, A2, A3. So these coefficient matrix we will write. Fine. So that is the coefficient matrix and B is the source terms. So source term in the sense. So in the problem we have seen that at station A the value of temperature is 100. Okay. At station B the value of temperature is 400. Okay. So when we do some arithmetic calculation and when we perform the, since it is delta x by 2, so at best phase as when we have seen, so that will be 200 Ta. Okay. So yeah, so that is 200 Ta and 200 Tb. Now you can see, so 300, 100. So basically these are the coefficients of A. Let's say AW or let's say AA and A2. Fine. So in the first equation, so let's say you take the point 1. So you have 2 and A. Let's say. So we are writing the value of the west node and the east node. So remaining 3 are not there. That's why we have taken 0. So into T1. So that will be the equation. So it is equal to the source term. Similarly, so for interior nodes, what we have? So this is the point of interest P, and this one minus 100 and minus 100. One is for west node, other one is east node. Point of interest P into T2 is equal to 0. So this is the source equation. So which you can see this one. So what is this equation? This equation which we are writing in terms of matrix term. So how? So that will be like minus A1 T1 plus A2 T2 minus A3 T3 is equal to 0. So here what is A1? 100 minus 100. So what is What is A2? A2 is nothing but it is 200. And what is A3? 100 actually. Okay, this is for second equation. Similarly, third equation, what do we have? For the third equation, there is no first term or there is no point of interest 1. For the third equation, we have second, third and fourth term. Okay. Next, for fourth equation, what we have? Third term is available, fourth term is available, fifth term is available. Similarly, for the fifth one, what happens? So, for the fifth one, so we have seen, for the fifth one, what we have seen? So, we have a wall here. Fine. So, when you take the grid point 5 here, so when you take the 4 here, so for the right boundary, so we apply a temperature boundary condition here. Fine. So, when you take the fourth one, so it is the neighboring point. So, this is what we have. So, point of interest, the left one, point of interest, and the right boundary, we have a source term which is 200 to be. So, what is happening when we have walls? So, here we can observe that. So, when we have some wall kind of phenomena, so we are taking the boundary condition as some AP values or we are taking as 0. Okay, the coefficient values we are taking it as 0. We are assuming it as 0. So that's why you have the source term. So here you can see clearly in the equation. Here you can see clearly in the equation where for the interior points. So let's say T2 to T4. So these are interior points. Okay, for the interior points, so there are nothing source terms. When you see the boundary points, so this point is for A and this point is for B. So when you see the boundary points, so we have the source terms. Fine. So that's why the equation, whatever we have, so for the first equation which is having the wall, so we apply AW for the best known as 0. Fine. So AW as 0. Similarly, for the right boundary, AE as 0. So what is the significance? What is happening? So when you are formulating the final volume formulations, when we have wall conditions on the other side, or let's say you have left hand side, you have one right hand side. So for the left hand side, we have a wall boundary A. For the right hand side, we have a wall boundary B. So therefore, for the left hand side, we have considered AW as 0. For the right hand side, AE as 0 because it is right boundary. Fine. Now, when you observe this matrix, let's see next slide. So when you observe this matrix, so what is happening? So this is called subdiagonal. So we have subdiagonal matrix. Okay. So you have super diagonal matrix. So you have diagonal matrix. So let's say this is diagonal matrix A and super diagonal B, C. So basically, here to invert the matrix of the let's say 5 cross 5 or 6 cross 6, what we have to do, we have to consider each element. Now, when we perform the upper triangle or the lower triangle matrix elements, then we can get the values of. So at the end, what we are getting, we need to get the value of T1, T2, T3, T4, T5. So what is the meaning of T1, T2, T3, T4, T5? So when we see the diagram, so the element is divided into 5 parts. So where the first one is basically is used for the initial grid point. Second one is the secondary, third. So when we are divided the element into 5 parts, so these first element temperature T1, second element temperature T2, third element temperature T3, fourth element temperature T4, fifth element temperature T5. So we are getting the values of T1, T2, T3, T4, T5 by inverting the matrix. Fine. So this is what we have from the matrix phenomena. Now to solve these forms, so basically this is called tridiagonal matrix. Why we say tridiagonal? So since we have one main diagonal, so basically, so this is called main diagonal. Okay, so this is super diagonal. Okay, and next we have other one sub diagonal. So we have super diagonal, we have main diagonal, we have sub diagonal. Fine. So these three are there. So when we do arithmetic operations in terms of lower triangle matrix or upper triangle matrix, so we can do determinant easily and solve the equations such that, so when we solve, what happened initially, the value of temperature is 400 T1, T2 is 220, T3 is 300, T4 it is 380, T5 it is 460. So how? So you can see here. So let us relate in realistic manner. So realistic manner is what we have. So here we have the left boundary. So where we have applied temperature 100. Here we have right boundary. We have 400. So when we actually apply this thing, so what is happening here? The values, you can see that as the diffusion has increased, so because of the temperature difference, so starting initially for let's draw here. So this is A1, this is A, this is B. Two, three, 4, 5. Okay. So 1, 2, 3, 4, 5. So this distance is delta x by 2. So this distance is delta x by 2. So this is motion. So here we are applying 100 Kelvin. So here we are applying some 400 Kelvin. So what is happening? So in reality, the physics, so whenever we perform any numerical simulation, so we have to actually check with the exact solution also. So this equation T1, T2, T3, T4 is computed with the finite volume approach in the numerical method. Okay, so we took a matrix and like we have taken element wise. So this is one element kind of thing. Next element is like this. So how when we see, so this is 1 W 2. This is the first element. So next element 1 and 2, 3. Second element. So we have 3, we have 4, we have 5. Yeah. So basically, sorry. So here it will be 2, here it will be 3. Here you have 4. Okay. Third element. Next we have 3, we have 4, 5. Fourth element and the fifth element. So we have 4, we have 5. So this is A actually, and this is B. So you can see this is first element, second element, third element, fourth element, fifth element. So we have divided a 1 meter rod into 5 elements. So when we are, there is no need of like let's say it's not that we have to take only 5 elements. We can take 10 elements. So if I take 10 elements, what happens? I will have each one has 0.1. So here you can see a rod of 1 meter. So for the 1 meter rod, so I divided into 5 elements, so that we got 0.2 meter. When I do it in 10 elements, so what happens? 0.1 meters. When I do it with 20 elements, so that will be, so let's say 1 meter divided by 20 elements, 0.05 meters. Let's say. So what happens actually as I'm increasing the points? Why I have taken only 5 points? So since I'm solving in the numerical method with the hand calculation, that's why to show you the matrix with the physical field, so we have taken only 5 points. So when you run the code, let's say using MATLAB, Python, C++, or any code, so when you're trying to solve it numerically, so the value of dividing the number of points n, you can go till let's say 1000 or 10,000, such that the accuracy of the simulation will be high. Accuracy, why accuracy actually? So if you take more number of points, the connectivity, and so you can see the first one is 140. So let's say this is 140. So next is like 200, 220. So next one is like 300. So there is the entity of the curve is not smooth actually. Okay, so it is what do you say? It is somewhere discontinued, like not discontinued. Like it is what do you say? It's kind of non-smooth in nature, where the points are less. Okay, so example, like if we draw the temperature versus x direction. So let's say at point 1 you have this. So at this. Okay. So like this the temperature may increase. So with a discontinuity or let's say some kind of non-smoothness, the curve will change. When I take more number of points, so here instead of going for 5 points, let's say I take 50 points, T50, so on, let's say T1, T2, T3, T4, T5, T6, T7, T8, T9, T10, so on till T50. So if I take 50 points, so the curve of temperature or the temperature profile with respect to X, let's say it has started some smooth nature. Okay, so if you take more number of points, so it will be very very smooth. Okay, so if I take less number of points, what is happening? So it has some what do you say, not smooth profile. So where for the 5 points, so let's say from point 1 to 2 you can see the variation, how much, nearly 80. Okay, so you have a bandwidth of 80 Kelvin. Fine. So between T1 to T2 you have 80 Kelvin, T2 to T3 you have 80 Kelvin, T3 to T4 you have 80 Kelvin, T4 to T5 you have 80 Kelvin. Now if I make, let's say here I have 5 points. If I make 50 points, so the difference between temperatures, let's say the first one you have 140. The T2 point, next T2 point will be 148. So next T3 point will be 156. Okay. So what's happening actually? So the amount of complexity or the smoothness is starting to increase. So when I take 100 points, it will become 4. When I take 200 points, it will become somewhat 2. So in the sense what? T1 is 140, T2 is 142, T3 is 144. So what I'm showing? So the profile with respect to X, I am showing some regularly, or let's say trying to draw in a smooth curve nature. So the main difference is when the solution will be same. Let's say at the end point at T5 the solution is 160, and T2, the T2 value 220, T3 value 300. So this may be same, but when you are trying to increase the point, so the accuracy will increase, and the smoothness of the graph between the temperature profile and the X will keep on. Okay, so this is what we have seen for the numerical problem, which is having the uh, diffusion equation. So where we have taken a 1D element. For the 1D element, we have seen the heat diffusion equation. For the heat diffusion equation, we had the left boundary, right boundary, temperature applied. So for that element, we have divided into 5 elements, and when we had applied that AP5, APTP, or let's say AP5P, so is equal to AW5W plus AE5E equation terminology for the interior nodes, which is 2, 3, 4. So we framed a matrix here. You have which, so when for the interior nodes, you can see that you have 3 coefficients. Okay, let's say A1, A2, A3, A2, A3, A4, A3, A4, A5. For the boundaries, you can see A1 and A5, A1 and A2. So here you can see A4 and A5. This is what we have. Fine. So for the boundaries, what we are having, we are missing with one node. So one, let's say, what is one node? Either for the boundary B, each node is missing. So therefore, AE is 0. For the west node, so what happened? Like the boundary is present, therefore AW is 0. Okay, so that's why for the row 1 you have only 2 elements, and similarly for row 5 again you have 2 elements, which is A1, A2. Okay, so this is like which is combination of the source term. Fine. So this is how we solve the finite volume formulation for the body diffusion equation. And in the next session, we will see in detail about the convection diffusion equation and their problems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.